Hello, I'm Wilker, and today we are going to talk about how to get autocomplete Explorer capabilities for Om.next graphs. For this tutorial, we are going to write a parser that interfaces with some parts of the Spotify API. To access the Spotify API, you need to go at their developer website and create an application. After you create the application, you can use your client ID and client secret to generate a token. With this token, we are going to do the API calls to Spotify. We will now use that token to try to call the Spotify API and get some artist information. Now it's time to wrap this call into a function. This function is going to take two arguments. The first one is going to be the environment. Later on, this is going to be the same environment that you used at Om.next. So we're going to use to get the token on this case. And on the right side, we set the inputs that we need for a function. And in this case, we need the artist ID. The next thing we have to do is to qualify the output keys that we got for the response. This is going to be important later for the indexing and autocompleting part, so just hang on. A very common operation you're going to have to do all the time is to namespace the keys. So I'm going to create a helper function to do just that. Okay, it's finally time for us to start to do the parser thing. To write the parser, we're going to use a library that I wrote called Paton. And Paton is a library on top of Om.next. Under the hood, it uses the Om.next query AST parsing to start the parsing process. Connect is the real tech behind it. It's going to enable us to do the autocompleting and enable us to write the parser in a way that we're going to do it now. Okay, so let's just write a parser, and not on parser, a Python parser. If you want to know more about the Python parser, just go to the documentation on the website. Although I think that with Connect, this is going to be a bit outdated. Not outdated in the sense that's going away, but in the sense that Python Connect is a higher level abstraction, and I think most people will just use this instead of using the raw parts that Python provides. But even Connect works on top of everything that Python provided before, so everything is staying there. Let's just try the parser. Why not? Call parser, we need to send a reader. And in this case, let's say just if we ask for hello, we want word. If you go like that and ask for hello, we should see word. Cool. Ask anything else, not found. Great. Anyhow, to do this, we're going to want the map reader. That's a very default reader, pretty much use it everywhere. You want the pconnect all reader. They have a couple of readers, but for now let's just use this. And to initiate our query, we have to make an index out of the information we already got. What you have to do here is just map this function. So let's create the indexes. And this is the index starts blank, and then you call a function to add something to the indexes. So in this case, we're gonna add that function, that resolver we wrote before. By the way, we'll start calling those functions resolvers. And by resolver, I mean a function that takes an environment map as the first argument, a map of inputs, we need named keys for the inputs, and outputs, also a set of keys. Always a set of keys, no lists here. If you need to export a list, you need to wrap that list into a key, into a map. So, given that said, we need to set that the input of this function will be a set of Spotify artist ID, because that's what we require to call this function, and we need to map the output. But what will I put here? Well, you should put the shape of the output of the function. Right now we just don't know the shape, not easily. We can write from this, but come on, we have an automated way to do it. This automated way is a helper function included on Om.next called dataShape. As the name suggests, you send it a data as like this one, and it will return just the keys of it. And it returns the keys in a nested fashion way, so you can describe nested rich structures. Then you can just get it as used as the output of the description to the indexes. The next thing we have to do is add the indexes to our environment, and let's add the token as well. Okay, and now we can start querying. Let's say, for example, you want to query for the Spotify artist ID with that ID we tried before, and you want to get that artist name. Let's see. And fair enough, we got the Beatles back. And let's just make a different call here to test if we like to get the genres as well. Fine. Okay. One thing you might notice is that we have to copy over the environment between the calls, and that can get annoying over time, since most of this should be very standard when you call our parser. So Python has support for plugins, and there is an environment plugin, so you can set the initial environment for the parser anytime it gets called. With this, we can remove those guys here. And let's try it in. Okay, they're working. The next step we have to do is to expose this parser through HTTP. And we are using a service from Pedestal. So let's create a graph route here. That's going to be a post. It will be like this, but with transit output. And let's call graph API. And on this, we want to get the transit params. We should import our parser, call it the transit params, and wrap into a ring response. Okay. Next, we have to start the server. Before we go test and explore the API, there's one more thing we have to do. In the parser, we have to add this placeholder reader with a plus sign. This is required because of the way OGE is structured. This might change in the future. To explore the graph, we're going to use this project called OGE. OGE stands for On Graph Explorer. To use that, you set the endpoint for your graph API here. In our case, we have an issue. Since this is an HTTPS page and our localhost is running on HTTP, the browser will not accept an HTTP here. To go around this, I'll do some tunneling. I'll use a service called ngrok to do the tunnel, but you can do it wherever you want. As an alternative, you can download the OGE and run locally. This way, you don't have to do any kind of tunneling or anything. for us, let's place it here. Okay, and by now it should download the indexes from the graph. Oh, if I place the URL correctly, it should download the indexes and it should autocomplete automatically. And as you can see, it completes for all the responses we set. If we try like images that has a join, it shows the attributes on that as well. And as you can see, if you follow along with that idea, you can get the autocomplete for free. But now it's time for us to discuss a little bit and understand how this works. To start understanding how this processing works, we must look at the indexes. Let's make it smaller so you can see more of it. And I would like us to make an exercise to follow along a query looking at the indexes to see how the information is retrieved. On Python, we have this notion of context that when you are in a node in some point in the graph, you have some sort of information available to you. When you are in the beginning of the query, let's say right here, if we would express the context, there would be a blank map. Because at this stage, I have no information at all about the context. I don't know anything. But then, if we follow the query and we start doing an ident query, and when you do that, connect will look at the idents index. This index is built in a way that every time you add some resolver that has an input with just one element, this means it's an ident, because as soon as I have this information, I'll be able to access all the other information on the output. So when you do that, it's like we change the context to be this. So now we have a sport artist ID with something. And then we use that context in the subquery. So on this case, when we ask for the ID, it tries to look in the context. Oh, do you have the ID? And since it already has the ID, the query returns immediately. It doesn't have to do any server-side fetching or anything. But on this case, let's say we want the name. And then when it tries to look in the context, it knows, oh, I don't have a name. And then it goes into this index, this OEF, that means output input function. Then it looks up for the artist name, the key we asked for, and says, fair enough, I have this key available. And then it looks at a map that shows the possible ways you can fetch this key. And currently, we have one way that requires a Spotify artist ID, which is available in your contacts. So it again calls this resolver to fetch that data. And then it extracts the name from it. But at the same time, if we do more stuff like RC generators, when it does that, it doesn't have to call twice. Because when it does a request like this in the resolver, it amplifies the context with the entire return of the resolver. So it does a merge between what gets from the resolver here and return now. So when it looks up for the chairs, this is going to be there already. So it doesn't have to do an extra hop. And this is how the connect process your query when you ask for the information. Another interesting indexes is the IO, that means input-output indexes. And this index goes from, oh, okay, if I have this information, I have this available. This is the index used to make the autocomplete that you see. And to make this more interesting, let's add an endpoint to get some artist top tracks. It's very much like the artist by ID, so I'll copy the function. It's probably going to be faster. For now, we're gonna set the country as hard-coded, but you have access to the environment, so you could get this from the parameters, but we are not covering this today. And just to try it out, let's call this with token of token. And as you can see, we got a lot of things. I'm going to do something similar of what we did the artist for the track. But here we got a collection of things. So remember, we always have to return a map. So to handle this case, we're gonna map all the results by the adapt track, but then we're going to call a hash map to place this inside a Spotify artist top tracks. So okay, yeah, it returned in the tracks, so we have to extract that. Okay, and as we did before, we can use that data shape helper function to get us the output shape. So there you go. And by looking at it, we can see that there's a track album here. And also a list of artists. So for the list of tracks, let's adapt the records. And let's do something similar for the album. By looking at it, it seems nice. It seems it's all cool, good and namespaced. So let's copy it. And we could just keep adding here, but to demonstrate how that would work on a real application, you would probably have an atom containing the indexes. So this could be an atom that starts blank, and we can write a function like add resolver, get scene options, and would swap the indexes. And now we can collocate our adds with our implementations. So we would input and yeah, that's it. Can get rid of those now. And here we deref it. Reload, let's take a look at the indexes. So it seems to be growing. Good. And let's see if we can get the top tracks for an artist here. On here it seems pretty bad to read, so let's try on the OGE. This is a hacky way to update the index, just update the URL a little bit. I'll try to make a better way later. But for now that should suffice, and you should see the top tracks here. Fair enough. And there's a lot of information. I just want to see the names of the musics. So there you go. We have the Beatles and the top tracks of it. For the next endpoint, we're going to implement the audio features. This will be a bit like the one to get the artist by ID, or you're going to get the audio features by the track ID. And as usual, I'm going to try to call the function first and see the result I get from it. Oh, but first you have to get some track ID. And as you can see, we have just a list of track features. I think we can namespace this one as a track. It'll be all good. And okay, let's try this out. We want to get like the balance of a music. Oh, you see, not updated. That hacky thing again. And now I have balance here. What you might find interesting is that in this context, since we have a track ID, that's the input of it, and that's why we can get this on the autocomplete. That's how it detects how those things relate to each other. You might have noticed this query took longer to run. And as your graph grows more and more complex, it will be harder and harder to keep track of what's going on. And to help with that, we can set up a profiler. To do this, we just need to add the profile plugin here. So first we have to import it. And then we add the plugin. Reload everything again. And now let's run the query with the profile information. And as you can see, the information gets provided and a flame graph can show you what took the time to load it. So you see the drop text itself took 456 milliseconds, but it took a lot of time because it had to get the valence for each song, because that needs to be a query for each item. Or if you just remove the valence and run again, you're going to see much faster. Another thing that might worth looking at is that right now, if we ask for something else, we see that for the idents we now have the track available. But if you look at the information here, you see there is only information about the audio analysis stuff, because we tell him how to fetch the audio analysis for a track ID, but we don't know how to track other information like the name. If we were to put this track ID here, for example, we don't get the name or everything. We could get all the information for, we have the information for the audio analysis, but we don't have any basic information about the track. We can fix that by implementing the track. Now let's try again. First do that hacky chop edit the indexes. And now it should be seen. Yes, we got the name. Name and energy. You see those are kind of separated requests because they track the profile differently. And if you ask for this and everything else for that track, we get the full information. Remember that when it calls the endpoint, it merges that information that comes from there into the current entity. So when we ask for the asterisk, we're asking for, please give me everything that you got so far. It's not going to try to resolve every missing piece. It's just get whatever is there. Another general recommendation that I like to leave here is to add the Python error plugin for your parser. Uh, by default, if some exception occurs during your parsing process, the entire thing will stop working. The error handler plugin makes those errors more local, so only that key will stop and the rest of the parser can continue working. And let's remember that the identities can be called from anywhere. So let's say if I want the artist ID here, and again I ask for the same artist, we get the name, and we look at the performance. If we look at here, you can see that to get their artist ID, it spent the time twice. In Python we have a feature for request caching, and Connect is integrated with that. So all you have to do to enable it is to add the request cache plugin. Let's see, 2.5 seconds. Try again. The more important, you see that one's gone because it doesn't have to. When you use the request cache plugin, every resolver is cached during that request. So that's a very fast, very short span cache, and it's very useful for these kinds of inner current caching. Thinking about how Connect works, I'd like to point out that this is a system that works entirely by establishing relationships between attributes. Other projects, the Python Connect and the OGE, are still actively working. For the OGE, we still need to make the mode here recognize more about the on-query syntax. Right now, it doesn't recognize parameters or union queries or mutations, and those are on the list, so they can be in the future auto-completed as well. And for the Python, I guess we still have a lot of optimizations that can be done. If you think about it, as you grow your system, we might have more and more and more pathways to get from one information to another. And you might be in cases where you have multiple options for the same path, for the same target attribute. And it would be interesting to work and see how we can optimize this, and it can work as a caching strategy or something. But that's a lot of, and I think I learned this attribute driven think direction, especially from spec. Closure spec is the first system that I know that encourages you to put the attributes as your primary way of specifying your information. Would also be cool, I guess, if we could just implement those indexes as libraries. Merging indexes of the Python Connect is a trivial operation. So you can imagine that you could import, if you want to integrate your graph with a Spotify graph, you could just require a library that has the Spotify indexes with the resolvers, and you can just merge with your own indexes. And then you can have a Spotify track attribute on your own database, or something that you can link with that, and suddenly all your databases are connected. But for that to work, we need to think very hard about how to name stuff, how you decide what's a good name for the attribute. And I think it all comes down to how large is the graph you are trying to write. If your graph is very small and has very few relationships, those names can be small. But as you grow, if you think internet-wise, and if you want to connect multiple big APIs on the internet, I think we better start to think about using those long names. And thank you very much for staying with me until the end of this video. See you on the next one. Bye.